So you might have noticed this yourself if you're using some of the newer AI models. You give them a tough problem, and they don't just instantly give you an answer. They
Mhm.
often seem to, well, show their work, generate this kind of internal monologue, that chain of thought thing, before the final output.
Mhm.
It really gives the impression they're, thinking it through.
It absolutely does, and that's a key feature of what people are calling large reasoning models, or LRMs. They're specifically designed, or maybe prompted, to produce those intermediate steps.
Right, aiming for a deeper process than just matching patterns.
Exactly, a more structured approach.
Which brings us neatly to the big question for this deep dive. Are they actually reasoning when they show their work like that? Fundamentally reasoning?
Or is it something else entirely? Maybe a very, very sophisticated imitation.
That's the core of it. And that's what this deep dive is all about today. We're using a specific, really interesting research paper to guide us.
Yep. Our mission here is to walk you through their findings. We want to understand the basic capabilities of these LRMs, see how they scale with problem complexity, and crucially, find out what their real limits are.
And they use a pretty unique experimental setup to do this.
A very clever one, yeah.
So the source material today is all built around this one paper. It's called The Illusion of Thinking: Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity.
Quite a title.
It is. And the researchers behind it felt, quite rightly, I think, that the usual ways we test AI, math problems, coding challenges, they have some issues.
Big issues. Data contamination is a major one.
Hmm.
The models might have just seen very similar problems or even the exact problems during their training on, like, the whole internet.
So they might just be remembering, not reasoning.
Precisely. But maybe even more important is that those standard tests, they usually just score the final answer,
Mm.
right or wrong.
They don't show you how the model got there.
Exactly. You don't see the process, or if it's genuinely thinking step by step.
Okay, so how do you get around that? How do you test for real reasoning if you suspect it might just be memorization or, faking the steps?
Well, that's where their approach comes in. Instead of those standard benchmarks, they use controlled puzzle environments.
Puzzles. Okay, why puzzles? What makes them better for this?
Well, puzzles are great because they give you really fine-grained control over complexity. You can take a puzzle, change just one small thing, like adding one more disc to a Tower of Hanoi,
Right.
and you know exactly how much harder that makes the problem mathematically in terms of the minimum steps needed to solve it.
And I guess because they can create unique puzzle setups the AI probably hasn't seen during training.
You pretty much sidestep that whole data contamination problem.
Got it.
The model has to rely just on the rules you explicitly give it in the prompt for that specific puzzle.
So it forces something closer to actual algorithmic reasoning, not just recalling patterns.
That's the goal. Plus, and this is really key, you can use simulators to check every single intermediate step the model generates in its thinking process.
Every step.
Every step, you can see exactly where it makes a right move, where it makes a wrong move, the whole trace.
So you can literally peek inside the thought process as it unfolds.
That's the idea. And they use 4 different kinds of puzzles to test different types of reasoning.
Okay, what were they? I think you mentioned Tower of Hanoi.
Yep, the classic Tower of Hanoi. Moving discs between pegs, that really tests planning and recursion, and its complexity explodes. It's exponential, something like 2 to the power of n-1 moves for n disks.
Oof. Gets hard fast.
Yeah.
What else?
They also use checker jumping. It's a simpler 1D puzzle swapping pieces with sliding and jumping rules. That one scales quadratically, so n+1 squared minus 1 moves. Less brutal than exponential, but still grows quickly.
Okay.
Then there was river crossing.
Hmm.
Think missionaries and cannibals, but generalized. It tests coordinating multiple agents under safety constraints.
Right. Don't leave the wrong combination alone on the riverbank.
Exactly. That kind of constraint, satisfaction, and coordination.
And the last one.
Box world. Stacking and unstacking blocks to reach a target configuration. This needs careful planning because of dependencies. You can't move a block if another one's on top.
Okay, so 4 distinct puzzles. Controlled complexity, no contamination, step-by-step verification. Who did they test with these?
They used some of the leading models out there, specifically the ones billed as large reasoning models, LLMs that have these built-in mechanisms like chain of thought or self-reflection capabilities.
You mean models like OpenAI's O3 Mini, DeepSeek R1, Claude 3.7, Sonnet Thinking, Gemini Thinking, those kinds.
Those are the ones mentioned. And importantly, for the really deep dive into the internal thinking process, they focused on models where they could actually access and analyze those intermediate thinking tokens.
So models like Claude 3.7, Sonnet Thinking, and DeepSeek R1 let you see that internal step-by-step generation.
That's right. That visibility was crucial for their analysis of the reasoning traces.
So they compared these LRMs with their thinking turned on, essentially, to their standard LLM versions without that explicit thinking process.
Using equivalent amounts of compute for a fair comparison.
Okay. And what did they find? Did the thinking always help?
That's where it gets really interesting. They found a core pattern. There seemed to be 3 distinct performance regimes, depending entirely on the complexity of the puzzle problem.
3 regimes. Okay, this sounds important. It's not just more thinking equals better answers.
Not at all. Let's take the first regime, low complexity. These are the really easy puzzles.
Okay.
Here, maybe surprisingly, the standard LLMs, the ones without the explicit thinking steps,
Yeah.
often actually performed better than the LRMs.
Better, without thinking.
Better accuracy, and they used fewer tokens, so they were more efficient too.
Wow. So for simple stuff, the extra thinking in LRMs was actually getting in the way. Like, it was a disadvantage.
It looks that way, overthinking perhaps, but then things shift when you get to the medium complexity regime.
This is where the problems are moderately hard.
Exactly. And here, that extra thinking effort, the chain of thought, or whatever mechanism the LRM uses, it starts to pay off. The LRM showed a clear accuracy advantage over the standard models.
Okay, so the thinking helps when things get a bit tricky. That makes intuitive sense.
It does. This is where those reasoning mechanisms seem to provide a real benefit in navigating the problem.
So low complexity, thinking hurts. Medium complexity, thinking helps. What about when the puzzles get really hard? The high complexity regime.
That's the third regime. And here, the finding was stark. Across every model they tested, both the standard LLMs and all the LRM's performance completely collapsed.
Collapsed. You mean like...
Accuracy just tanks.
Yeah.
Drops straight to 0. If you look at their figure 4 and figure 5, you see this pattern clearly.
0 accuracy. So beyond a certain point, none of them could solve the puzzle anymore, like hitting a wall.
A hard wall, exactly. For each puzzle type, there's a complexity threshold, and beyond that, failure is basically guaranteed for these models.
And this isn't just them running out of time or like hitting a token limit for their thinking process.
That's one of the most fascinating and maybe counterintuitive findings in the paper. As the problems get harder and approach that critical point where performance is about to collapse, the models actually start reducing the amount of thinking they do. They use fewer thinking tokens.
Wait, hang on. The problem gets harder. They're about to fail completely, and they think less, even if they have the token budget available to think more.
Exactly. It seems completely backward, doesn't it?
It really does. Why would they do that?
Well, their figure 6 bottom and figure 13 illustrate this pretty dramatically. A significant drop in the number of thinking tokens used right near that collapse point. And what this suggests is that the failure isn't just because they didn't have enough computational space or tokens to think it through. It points towards something more fundamental.
Like a limitation in their actual reasoning ability.
Yes, a fundamental scaling limitation of their reasoning capability when faced with increasing problem complexity. It's like they reach a point where the necessary logical steps are just beyond them. And maybe they even sort of give up trying so hard internally.
Wow. That's a big deal. It's not just needing a bigger engine. It's like the engine itself can't handle that kind of track.
It's a good analogy.
Yeah.
And because they could actually look inside those reasoning traces, the step-by-step thinking.
Right. The puzzles let them do that.
They could analyze how this failure happened and what the internal process looked like at different complexity levels. They mentioned figure 1 top and figure 7a showing examples.
So what did the thoughts look like? Did they see patterns?
Oh, definitely. Remember how for the simple problems, the LRMs sometimes did worse?
Yeah, the standard LLMs were better.
Well, looking inside, they often found that the LRM actually generated the correct solution quite early in its thinking process.
Okay, so it found the answer.
But then it kept going. It continued generating steps, exploring incorrect alternatives, getting lost down wrong paths after it had already found the right one.
So that's the overthinking they talk about. It finds the answer, then confuses itself.
Exactly that. Figure 7b shows this really clearly. For simple problems, like Tower of Hanoi with just 1 to 3 disks, the accuracy of the steps within the thought process actually goes down over time.
It gets worse the longer it thinks. That's wasted effort.
Completely wasted compute,
Yeah,
exploring bad ideas after solving it.
Okay, what about the medium complexity zone, where the LRMs did better?
In that sweet spot, the correct solutions tended to show up later in the thinking trace. The model explores some wrong turns first, but the extended thinking process eventually leads it to the right answer.
So the thinking is actually productive there, helping navigate.
Correct. The effort pays off.
And then high complexity, where they collapse. What's happening inside then?
Total breakdown. The internal trace just doesn't contain any correct solutions or even viable paths towards one. The whole reasoning process seems to fall apart when the problem complexity goes beyond that critical threshold.
Looking at those internal steps really paints a picture, doesn't it? You see the inefficiency, the limits, even when it's trying to think.
Absolutely. And this study also dug up some other findings that were frankly quite surprising. Things that really challenge our assumptions about what these LRMs can do, especially when it comes to robust, generalizable logic.
Like what? Give me an example. What was really unexpected?
Okay, one of the most striking ones was how they handled explicit algorithms. Take Tower of Hanoi again. The researchers actually gave the model the exact step-by-step recursive algorithm for solving it, right there in the prompt.
They gave it the recipe, the perfect instructions. You'd think it would just follow them.
That's what you'd naturally expect, right? Just execute the code.
Yeah.
But no, look at their figure 8a and 8b. Giving the model the explicit algorithm made basically no difference to its performance. No difference.
Nope. The accuracy collapse still happened at roughly the same complexity level. It didn't help them solve harder versions of the puzzle. It didn't push that wall back at all.
That is genuinely weird. It really makes you question if they're executing logic in the way a computer program or even a human following instructions would.
It certainly raises deep questions about the nature of their processing. Are they truly following logical steps, or just generating text that looks like logical steps based on patterns?
What else was surprising?
Another big one was how inconsistent the reasoning seemed across different types of puzzles. This is shown in figure 8c and 8p.
Inconsistent how?
Okay, take the Claude 3.7 Sonnet thinking model again. On Tower of Hanoi, for N10 disks, it could sometimes produce incredibly long sequences of correct moves, like over 100 correct steps in a row before making a mistake.
Wow, over 100 steps. That sounds like pretty sustained, complex reasoning.
It does, right? Seems impressive. But then they tested the same model on the river crossing puzzle for N3 players, which only needs 11 optimal moves to solve. Yeah. A much shorter solution.
The model failed much, much earlier. Sometimes they made a mistake by move 4.
Hold on. Over 100 perfect moves on one complex puzzle, but failing after just 4 moves on another simpler, shorter puzzle.
Exactly.
What does that tell you? That doesn't seem like consistent reasoning ability.
It really suggests that performance isn't just tied to the raw number of steps or the logical depth required. It might have more to do with how similar the puzzle structure is to things the model saw extensively during training.
So maybe it's really good at Tower of Hanoi because it saw tons of examples like it, but river crossing is less common, so its reasoning is more brittle there.
That's a strong possibility this finding points towards. It raises serious questions about how well these reasoning capabilities truly generalize to novel problem types versus relying on pattern matching or, near memorization from the training data, even if the specific puzzle instance is new.
So the reasoning might be less general than it appears?
It might be less stable too. Figure 12, another interesting chart, shows that while the thinking models fail later, on average, than non-thinking ones, their failure points show much higher variance. They're less predictable in where they break down across different problems.
Okay, let's try and pull all these threads together. We've covered the setup, the 3 regimes, the collapse, the weirdness inside the thinking. What's the main takeaway about these large reasoning models and their apparent thinking?
Well, this deep dive, grounded in this paper's really rigorous puzzle-based approach, gives us a much clearer, maybe more sobering picture than just looking at benchmark scores.
Right.
It shows that, yes, LRMs do seem to offer an advantage when problems hit a certain moderate complexity. That thinking process helps.
But
they hit fundamental barriers when complexity gets high. Hard walls.
And they struggle with generalizing that reasoning consistently. They can't seem to reliably use explicit instructions or algorithms you give them.
Their reasoning performance is surprisingly inconsistent across different types of problems.
And that bizarre finding that they think less right when the problem gets critically hard.
All of this points to significant limitations. It suggests their reasoning might not be as deep, robust, or general as the term implies, or at least not yet.
So for you listening, this study kind of cuts through some of the hype. It gives concrete examples and data showing where the current magic of AI reasoning starts to break down.
It helps frame the current state of the art. What does thinking actually mean for these models today? What are its boundaries?
So summing it all up, the research systematically probed LRM reasoning using these puzzles and revealed these distinct performance phases, a very clear collapse point at high complexity, and these quite surprising limitations in executing exact procedures and maintaining consistent performance.
Yeah, it really raises some crucial questions about how deep their reasoning truly goes and how generalizable it really is.
And that leaves us and you with a couple of really interesting, maybe provocative thoughts to chew on. First, think about that finding with the Tower of Hanoi algorithm. They gave the model the exact instructions,
The perfect recursive solution.
and it didn't help. Performance didn't improve. The collapse happened at the same point. What does that really tell us about whether these systems are executing logic in a robust, step-by-step way we'd recognize?
Or is their process something fundamentally different, more about pattern generation that mimics logic?
Right. And then there's that stark inconsistency, over 100 correct moves possible on one complex puzzle.
But failing after just 4 moves on another, much shorter puzzle.
What does that inconsistency across problem types suggest about the nature of their ability? Is it pure abstract reasoning?
Or is it perhaps much more tied to the specific structures and statistical patterns they absorbed from their massive training data? How much is true generalization versus sophisticated pattern matching?
This deep dive has given you a much closer look, based on this specific research, at the frontiers and, importantly, the limitations of AI reasoning today. What new questions does this raise for you about how these incredibly powerful models actually think?